Hello students, welcome back once again to your physics class. In this today's video, I am going to talk about an important point, and that is Lorentz force. Already I have discussed in the classroom that what is the meaning of Lorentz force. That when a charged particle is entering into the perpendicular magnetic field, then how the charged particle experiences force, that already we have seen. In this today's lecture, we are going to discuss about the force acting on a current carrying conductor or on a current carrying wire. Okay, so before starting that, let's have a quick recap. First of all, already we have seen that when a charged particle moves in a perpendicular magnetic field, it experiences force. I have tried to show that animation here. You see it carefully. Let us say we are having such type of magnetic field, and in this magnetic field a charged particle is entering something like this. Okay, now as it enters in the magnetic field, what will happen? It start to rotate, it start to perform circular motion as I have shown here. Okay, now you can see there the charged particle is moving, but make one thing very clear here: this charged particle is isolated. It is a single charged particle only. When we are talking about a conductor, when we are talking about a wire, the conditions are totally different. The wire consisting that electron can experience the force as a whole, or the charged particles confined in the wire, they are not now making the motion something like this, whatever I have shown here. Okay, so our main intention is that to find out the force acting on the current carrying wire now, means charges are confined in the wire now. Okay, now let's see here. Further, we have seen that the force can be given by Fm is equal to q v cross b, where v is the velocity of the charged particle with which it is entering in that magnetic field. Okay, and Fm, that is magnetic force, it is given by as the v cross b, or the cross product of v and b here. B is the magnetic field which we are applying here, right? Let's go ahead and we will see now force on a current carrying wire in the magnetic field. So let us say that we are having such type of wire, and say this wire is kept in the perpendicular magnetic field like this. Let us say that the current in the wire is passing in upward direction like this. You can see in the diagram. Okay, so let us say that this current is I, and the field which we are applying here is, suppose here, capital B. Let us say that B is the magnetic field. Okay, so we are having a wire. Okay, and that wire is kept in the crossed magnetic field or the perpendicular magnetic field like this. Okay, we want to find out the force acting on the wire. So we will take this derivation in a simple way here. We are not going to take it in complex way. I will take a simple situation here. I will take a simple condition here. What is that? See here, I will start with the Lorentz force itself, but before that, let us say that the length of this wire is, suppose, L. Whatever segment I am considering here, it is suppose having the length L here. Okay, so according to Lorentz force, just now I have discussed, what is that? Lorentz force says that Fm is equal to q v cross b. That is the definition from Lorentz force for a single charge. So since here the magnetic field and the length both are perpendicular, or say velocity and magnetic field both are perpendicular, so this can be simply written as, let us say, sum as F equal to q v b. If you solve q v cross b, it will be q v b sine of theta. Theta is 90 here, that's why it is sine of 90, and sine 90 is 1. So that's why I can write simply force as q v b. Right, now what we will do here, we will try to replace the values of q and v here. Okay, how? See, we have F equal to, now this q is replaced. If you can see the mouse pointer, see here, this is it. Definition for current is q upon t, right? So from there, if I write the value of q, it will become I into t. So that's why this is I into t. Let us say that the charged particle is taking time t to go from bottom to the top. Let us say that the time required for the charged particle is, suppose here, t. and it is covering the distance of L, then the velocity or the speed, say rather here, of the charged particle can be given by L upon T, right? So from there, if I put the value of V, it becomes L upon T into B. Now simplified, TT will be get cancelled out, and simply you will remain with the F equal to ILB. Okay. Now that I into L, that can be taken as a current carrying part, current carrying element. If I take a small part, I can write that L as DL also. Okay. So here you can see L can be taken as a vector, B is also a vector. If I continue with the sin theta part from the previous equation, I can simply write this F as, say now Fm again, it is I L cross B. Fm is equal to I L cross B. So direction of this force will be perpendicular to the plane containing length and magnetic field here. Now in this case, if I think, direction will be inward here. You can see in the diagram I am showing here a cross mark. Okay, so that is indicating direction. That cross mark stands for that the force is inward within the plane of this diagram or this plane of this frame. Okay, so in this way we can find out the force acting on the current carrying wire or current carrying element. So I think this is okay for this article. Take care. We'll stop here. Bye.